For this last section of section 7.3, we're talking about the central limit theorem. Most population distributions are not normal. So what is the shape of a sampling distribution of sample means when the population distribution isn't normal? You may be surprised to find out that as the sample size increases, the distribution of sample means changes its shapes. It looks less like that of the population and more like a normal distribution. When the sample is large enough, the distribution of sample means is very close to normal, no matter what shape the population distribution has, as long as the population has a finite standard deviation. So if we draw an SRS of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem says that when n is large, the sampling distribution of sample means, x bar, is approximately normal. Consider this strange population distribution from the Rice University sampling distribution applet. Describe the shape of the sampling distribution as n increases. What do you notice? So you can see the bigger our sample size. First we have n equals 2, then n equals 5, getting closer and closer to normal. N equals 10, and n equals 25. Look how normal it looks when we get to n equals 25. Here's another population distribution with a strange shape. Same thing. The higher the sample, the more closely it resembles a normal curve. So as the example illustrates, even when the population distribution is very non-normal, the sampling distribution of the sample mean often looks approximately normal with sample size as small as n equals 25. If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what sample size is. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. So that's a rule that we have to remember. The central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. Very powerful. Okay, so let's look at example on the last page of your packet, which is page 27, according to me. It says, suppose that the number of texts sent during a typical day by students at a particular high school follows a right-skewed distribution with a mean of 45 and a standard deviation of 35. How likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts in the last day? Okay, so let's write down what we know. We know that mu for this population is equal to 45. We know that the standard deviation of the population is equal to 35. We're going to let x bar be the average number of texts for 50 randomly selected students. Our goal here is we want to find out what's the probability, or how likely is it that 50 students will have sent more than a total of 2,500 texts in the last day. So what's the probability that x bar is greater than 2,500 divided by 50? Because we have 50 total people, right, in the population, so that actually works out to 50 texts per person. So we're really trying to find out the probability that x bar is greater than 50 for each person. Okay, since we're talking about a sample mean, we have mu of the sampling distribution is going to equal mu, so that's going to equal 45. the standard deviation of the sampling distribution is going to equal the standard deviation of the population divided by the square root of n, and we get 35 divided by the square root of 50, which I got 4.95. And again, we should check that it says at a high school, we can assume that 50, n equal to 50, is less than 10% of all students at the school. Okay, so the 10% rule works, so we can find the standard deviation, and since n is equal to 50, we're allowed to use an approximate normal distribution, which is greater than or equal to 30. We can say we have a normal distribution with a mean of 45 and a standard deviation of 4.95. Okay, so now I got to find my z-score to finish this problem out. So I'm going to find z, which is 50 minus the mean divided by the standard deviation, and I got 1.01. So really up here I have the probability that z is greater than 1.01. If we use our back of the book, we would have to take 1 minus the number from the book, and we get 0.1562. If we use technology, remember you can write normal CDF on your paper, and we'd have to put 50, 1,000, 45, 4.95. And that also gives us an area of 0.1562. So to conclude, and I'm running out of room, so we would write this out, but we would conclude with there's about a 16% chance that a random sample of 50 students will have sent over 2,500 texts in the last day. Okay. Questions, comments, concerns, write them down, bring them to class. I hope you're excited that now we have finished Chapter 7, so you know what that means. We'll be getting ready for our tests next week.